All right, let's get started.
Yes, sir.
For the first question, we have right. So I'm given a function which is defined as follows. And the question is discuss the continuity of f. So take a few minutes, maybe around 8-7, we'll resume discussion. All of you solve this question, and at 8-7, we'll discuss what ideas everyone has. All right, what are the answers?
At mine, f is not continuous at -2.
Okay,
Continuous at 0 and 3, sir.
-2, 0, 3, and what about other points?
Doesn't
Could you repeat? I couldn't hear you.
I'm saying at -2, it is not continuous, I think.
That's okay. F is not continuous at x is equal to minus 2. But when you're asked what is discuss the continuity of f, you have to talk about every point. So, okay, at minus 2, it's not continuous. What about the other points?
0 and 3 are continuous.
But is it okay if I write this? Continuous everywhere else. That is x not equal to minus 2. Is that okay?
I'm still
Yes, sir.
solving, so I can't conclude that.
Okay. Even I don't know. But let us say minus 2, 0, and 3. What about other points? What about points which are not minus 2, 0, or 3? Is the function continuous or not at points other than
So
these three
greater than
points?
0 is continuous, I think so.
Okay, so how do you justify that? So for example, let's say at x equal to 4. Why is the function continuous at x equal to 4?
Because it has same function for left, right, limit and function.
So it's a polynomial function at x equal to 4. It's a polynomial function and it's not changing at x equal to. At x equal to 3, for instance, on one side it is one polynomial function and on the other side it is a different polynomial function. That is why we should be careful about those points. But whenever it is defined as a polynomial function within the neighborhood of a certain point, there you don't need to check. You know that polynomials are continuous functions, right? So the only, as far as the solution goes, so this is what I got. This is not what I'm saying is correct. So let me write the solution now. For x not equal to minus 2, 0, or 3, f is continuous. This you don't need to check. You can directly say, because it is either the modulus function or the or some polynomial function, and it stays the same way in the vicinity of a point. But at minus 2, 0, and 3, the behavior changes. So to the left of minus 3, that is x less than, minus 2. How does the function behave? Modulus of x plus 1, right? F of x is modulus of x plus 1. So what is limit as x goes to minus 2 minus f of x? This would be limit as x goes to minus 2 minus of modulus of x plus 1. How would I compute this limit? I can do it directly by substitution, right? And what is the value?
Minus 2 plus 1, that is minus 1 mod minus 1, which is
1, sir.
1. Right. So left hand limit at minus 2. This is not standard terminology, so I just leave it. This is minus 2 minus f of x is equal to 1. What is the value of f of minus 2? as per the definition?
2x plus
Minus
3,
1.
that function will satisfy, which is minus 1.
Is that okay? But are these two equal? No. So left-hand limit of the function at -2 exists, but is not equal to the function value at that point. So directly from here, you can conclude, of course, that the function is not continuous at -2. But just for completion,
Yes,
let's
you have
do
made a
the
mistake.
right hand.
Yes, yes. Sorry.
What is the mistake?
No. I thought I didn't saw f of -2 is -1.
Now, if I want to compute the right-hand limit, where I'm approaching -2 from the positive side, positive meaning the right side of -2. What is the behavior of the function as to the right of -2? It is the second expression, which is
That
2x
is
plus
also
3.
2x plus 3. Here also -1.
Here again, if you substitute, you will just get -1. Since it's a polynomial function, the one-sided limit will be equal to the function value wherever the function is included, whichever side is included. In this case, it is the right side which is included. So here you have at x is equal to -2, LHL is 1 and RHL is equal to f of -2 is equal to -1. So clearly LHL is not equal to RHL, so or LHL is not equal to function value, therefore f is discontinuous. At -1. Of course, this is the proper way to solve it. In an exam, in the interest of speed, you should be doing it much quicker. Just substitute the value on either side, since there's no problematic term. So if this was something like 2x plus 3 divided by x minus x plus 2, then it would have been problematic. The right-hand limit does not exist and so on. But here it is all well-behaved functions, polynomial functions. So the computation of the limit just involves substituting the value in the expression, and you'll have no problems. So this is about, so let's do it faster for the other points of interest. So this was for case 1, x is equal to -2. So we have resolved that case. Case 2, x is equal to 0. What is the LHL at 0? It is limit as x goes to 0 minus, to the left of 0, I have 2x
3.
plus 3. So this would be 3. What is RHL?
It is also 3.
To the right of 0, the function value is x plus 3. So again, once I substitute, I will get this, and f of 0, which is included in the third definition, that is x plus 3. That also happens to be 3. So all of these things are equal. Therefore, I just express itself. So f is continuous at x is equal to 0. So typically, you should do this at least as fast as this or faster once you have a good amount of practice. Otherwise, you take your time. At least in the beginning, you can afford to take time. But in the exam, there might be more difficult questions, so you have to optimize where you use your time.
Query, if I can raise.
Yeah.
So
Yeah, sure.
I got the LHL and RHL of f of 0, But at
Mhm.
f of 0, like the function, we can either take 2x plus 3 and put x is 0, then we can find f0, or else we
No,
can
so
do.
here you see in the definition of the function, you have not included 0 in both sides. It is defined
Acha,
as 2x
acha,
plus
oh,
3
I missed.
for
Okay, my
closed to
miss.
open 0.
Okay, I missed that.
So
I written it.
it's the same thing over here also.
Yeah, I got it.
Typically,
F0.
any value of the domain will be included in only one of the intervals of definition. Otherwise, so suppose uh, instead I put this as less than or equal to, this won't even be a function, right? Because if I compute f of minus 2 using the first definition, you will get 1. And if I compute it using the second definition, I'll get minus 1. So you'll have a situation where this minus 2 is mapped to 1 and minus 1. So this is not a function. So this fails to be well defined in the first place. So whenever you are given piecewise functions, these are called piecewise functions. So the values of the domain, they will be typically included only in one piece. For the specific case of x is equal to 0, it is included in this piece. So here you are minus infinity to minus 2. Here you have 2 to 0. Here you have 0 to 3. And this is 3 to infinity. All of these are disjoint intervals, and together they cover your whole domain. Is that fine? Your query is answered, right? Okay. So the last case is x is equal to 3. LHL is limit as x goes to 3 minus f of x to the left of 3 is
12.
x squared plus 3. So this would directly become 12. RHL, which also happens to be f of, okay, let's not do that jump. To the right of 3, you have x cubed minus 15.
25 minus 15, 12.
27 minus 15, which is 12. And then f of 3 is also 3 cubed. So it's the same thing. Even over here, 3 is included only in this part of the definition, not in the above one. So we use 3 cubed minus 15 to get 12. This is equal to this is equal to this. Therefore, f is continuous at x is equal to 3. So this solution that was given is correct. Does anyone have any doubt in any part of the question?
No, sir.
Since differentiability is also covered, can you take a couple of minutes and say at what points is the function differentiable and at what points it is not?
If the left hand and right hand derivative exist, then only it's differentiable.
Can you give me the points? Take your time, figure it out, and tell me the points at which it is not differentiable, for instance. Does anyone have the set of points at which this function is differentiable or not differentiable?
Computing.
It's not differentiable at any point.
Why not things like -1? I'm supposing you're implying among those three, right?
Because if we differentiate and substitute the value, means it may give different value for f of x nu, so that
No. So what I'm saying is, what about at x equal to 1, for instance? Is it differentiable or not?
Sir, I have a
I
doubt.
think it would be differentiable because at -2 right hand left hand derivative does not exist. At 3 also LHD or HD does not exist. I'm yet to compute about 0. So I guess in one region, I think it would be differentiable. It's just a hunch.
In any of these interior points, wait, whatever.
It's just a hunch.
Once again, in these intervals, you're good because it is defined as a polynomial function. Polynomial functions are differentiable. What can happen at those points is that there can be a corner in the graph, speaking in the context of the graph. So that is what you have to check. But there is one tricky thing over here. This is also a modulus function. Modulus function usually has a corner point, even though it is continuous. Does that corner point belong to that domain? That is something that you have to check. So maybe we'll come back to this question at the end. The answer is differentiable at all points other than -2, 0, and 3.
Sir, can you explain it now?
For differentiability, I'll give you a diagram, and the theoretical proof I'll give at the end. So how have we defined the function? Okay. You have this -2, have 0, and you have somewhere 3. So before -2, what is the function? It is modulus of x plus 1. What is modulus of x plus 1? It is actually just -x minus 1 in this interval. So it would be at -2, it's 1. So approximately center here, and it will be something like this. And then this is not included. So I'll just put a circle over there. And what is it defined as after that? It's 2x plus 3. 2x plus 3 starts at -1. It's at line of slope 2 all the way up until 0, at which point it will reach the point 1, 2, 3, something like this approximately. Right. Once again, this point is not included, but it will not make a difference because the next behavior is x squared plus 3. So here it is 2x plus 3 in this interval. Next, you have x squared plus 3, which looks like the parabola right until this point. Just assume that this is the point 12. And after that, it is x cubed minus 50. It's a cubic function. So x cubed goes like this. If I do minus 15, it goes in a way that the cubic function would. It'll be a sharper, more slope thing. Probably not like this at this point. I'm not sure. But it'll definitely have a corner-like behavior. To check why that is not differentiable, what you need to do is remember that the definition of differentiability is you have to look at this limit. At the point x, if you want to check the differentiability, this is the limit that you have to compute. At each of the points -2, 0, and 3, what is going on? This limit, when you're computing, you can approach h from negative or positive. So you can take those two directions and check the limit. So first of all, at -2, you can automatically say it's not differentiable because it's not continuous. Continuity is minimum for differentiability. So this thing is not differentiable is immediate. At 0 and 3, it is continuous. So you have to do the check. So let me do limit as h goes to 0 minus f of 0 plus h. I'm checking differentiability at the point 0. So I'm approaching 0 from this, and I'm approaching 0 from the other side. Now, in both cases, f of 0 is 3. So this first limit, the left-hand limit, would be f of h. But h, you see, you are on the left of 0. So it is 2h plus 3 minus 3, 3 being coming from f of 0 divided by h. And for the right-hand limit, it is f of 0 plus h, or f of h, where h is positive. So this would be h squared plus 3 minus 3 divided by h. Now the first limit will become 2. I'll let you check that. And the second limit will become 0. And this is what I assume you were saying, left-hand derivative and right-hand derivative. Clearly, these two are not equal. So the limit of this expression at the point x is equal to 0 does not exist. So it's not differentiable. Graphically, also, you can see that there is a corner. Whenever there is a corner, you will not have differentiability. As we saw over here, it might not be immediate just by looking at the function, what the graph might look like.
If I may say something.
Yeah.
So what I done at x is equal to 0. So basically I took an right-hand derivative. So I computed f dash x and then put x is 0, which gives me LHD as 2. And for
That you should not do usually.
Okay.
Because of the thing that we were, I would ask you to go and look at our discussion in the summary session about this function. So here, if you want to talk about differentiability at 0, if you just say I will differentiate this expression and take the limit as it goes to 0 from the left or from the right, So you'll get something like cos of 1 by x. If you differentiate this expression using the product rule, what you will get is 2x sine 1 by something like this. Okay, and this does not have a limit, but the differential actually exists. So you have to do it by first principle. In this case, what has happened is this function is very well behaved. It's a polynomial function. So the derivative is also continuous. So, but that need not always be the case.
At 1 will
So
be, is it function differentiable at 1?
yeah, so at 1 here, in the vicinity of 1, so differentiability is a local concept. Okay, so if it is defined as a polynomial in a neighborhood of a point,
Hmm.
then you can automatically say it is differentiable. So even if you go back to first principle,
I'm sorry, sir. What does that statement mean exactly?
okay, so if I have a function that might get into things more serious than what is there in the course, this I will revisit only at the end. Okay, so it might have already become too complicated, but this is the right way to compute the derivative, compute the left-hand derivative, compute the limit of this expression by substituting the point of interest in the place of x and take this limit exists if the right hand limit and the left hand limit are equal. And in this case, we have seen that the function is defined in different ways on the left and the right. And when I substitute and compute the limit, you get different answers. So it's not differentiable. What I meant by differentiability is a local thing. I'll tell at the end. That is somewhat out of the scope of the syllabus or what this course wants to say. And it might be confusing for everyone, at least for people who are seeing the formal definitions for the first time. Okay, so this is just a reference for why you should not use f prime x is equal to, so you are doing something like this, right? F prime at x naught is, this is essentially what you are doing, correct?
Mhm.
So that's not always the case. So what would this mean? This would mean that the derivative function is also a continuous function at that point. That need not be true. Whenever there are piecewise functions, always go back to first principle. Okay, so this one, I'll write this as a remark, differentiability, even continuity for that matter, is local. I'll come back to this later because we need to solve more problems. So the second question is something that you would commonly encounter in exams. And we have done this in summary session as well. We can take one more of this. So this is a function which is defined from 0 to infinity. Find a and b such that f is continuous at every point, continuous. So when I say continuous on an interval or on a set, it means that it is continuous at every point on the set. 8:41, we'll resume discussion. Take your time, find the values of A and what are the answers?
A minus 1, B plus
So
minus 1.
minus 1, 1.
Let us quickly go through the solution. So any one of the people who answered this question, can you walk me through the solution?
We check on points like x equal to 1 and x equal to root 2. Continue.
Okay. Continue to dictate that this should be equal to this. So what are each of the quantities? What is the left hand limit?
X square upon A.
And the
X square upon A at x equal to minus 1. So sorry, at x equal to 1. So that will be 1 by A. I'm skipping a few steps now that we are a little bit more comfortable. To the right of A,
Minus
it's identically minus 1, which is equal to the function value also quite trivially. So this gives me A is equal to minus 1. Similar thing we'll do for this. Left hand limit is equal to the right hand limit. Yeah, right. To the left of root 2, the function behaves like a constant function. So this is minus 1. What is the right hand limit?
2b square minus 4b upon 2.
Which is also equal to the function value at that point. even though there is a denominator term, the denominator is not vanishing anywhere in that interval, root 2 to infinity. So we are good. Yeah, sorry, two. Sorry. Yeah. And now what happens when I rearrange and write it out? How would I solve this quadratic equation?
Factorization.
Can directly say that this is b minus 1 the whole square, since we know that identity. Factorization, or even if you want to use the formula, anything works. All of them are correct. This will give me b is equal to 1. Now, if this was not a quadratic equation with equal roots, or if this was a quadratic equation with discriminant to be negative, so let's take that case. What would your concluding line be if the discriminant of this equation was negative?
And it is always negative.
Could you repeat that? I couldn't hear you clearly.
So can you ask again?
So suppose in place of this equation, what if you had got something like b square minus 2b plus 9 or whatever, it's 10 equal to 0. So suppose the function, it was defined in a different way and you ended up getting this as your quadratic equation. At this stage, instead of b square minus 2b plus 1 equal to 0, suppose you got b square minus 2b plus 10 is equal to
Minus
0.
b plus or minus root b square minus
no
4ac
real
by
roots?
2a.
Yeah, but then when you do b square minus 4ac, you see that it is 4 minus 40, which is minus 36. So there are no real roots. That is correct. But what does it mean for the given question? So the given question asks you to find a and b such that we have continuity.
There does
So
not
what is the
exist
conclusion?
any b.
Yeah. So for no value of b will this function be continuous. All right. So that can also, I mean, that exam, I don't know how the question would be formulated for that to happen, but yeah, that's also a possibility. Just because you have some constants in the equation doesn't mean there always exist solutions which would make this continuous. In this case, it does, and in this case, it is unique. If there were distinct roots, then there could be two different possible values of b for which the function defined using this formula is continuous. Any doubts? This one. So here the slope will be actually sharper. So I'll let me draw that. It will be higher the slope. That maybe we'll get back to at the end. So is this question all right for everyone? A is equal to -1 and b is equal to 1. So this is correct. Then we go to the next question.
Yes.
So for the third question, you have it's a similar question. Just do it very quickly and let me. This you should be able to do very quickly. I'll not wait for any time. So whoever gets the answer first, you can just let me know.
Zero.
So I'll quickly write out the solution. The left-hand limit at 1 is a plus 1. The function value is 3. The right-hand limit is b plus 1. So both a is equal to b is equal to 2. So this is correct. A minus b is equal to 0. And I'll write question 4 over here. So maybe one of the last questions on continuity. This is as we have been doing so far. In order to get the solution to this, we need limit as x goes to minus f of x. We need to discuss the continuity. So let us write those two things separately and f of 2. So can you tell me what each of these quantities are and why they are so very shortly?
1, 2, 2.
Which is 1?
First is 1.
This is 1, this is 2, this is 2.
Yes.
I think all are 2.
All are two, sir.
All are 2. Because at 2, you are approaching 2 from the left hand. So anyhow, it is taking positive value of 2. Another is a
Yeah, it's just mod x, right? So here it is just mod x. So when I substitute 2, I'll get 2. Here it is floor of x. And for any point above 2, within between 2 and 3, near 2 and above 2, it is 2. And the function value at 2 is anyway given to be. Just substitute this. What would the graph look like? Roughly, it is mod x until some point. So you'll have this V-shaped graph until 2. And then it becomes like the floor. Something like this. Now, at what points is it not differentiable? So here, there is one more thing. Are there not other points
Not
that we have
continuous
to talk
at
about?
3, 4, 5, sir. Not continuous at 3, 4 infinity.
Not continuous at 3, 4, 5, so on. Or which is the same as natural numbers minus 0, 1. So even though on first glance, it looks only as if 2 is a point of interest, you need to be careful. Because this function itself, somewhat by definition, even though it is defined in just one way, that one way itself is discontinuous at all integer points. But within the domain, within the domain of this, the integer points are only 3, 4, and greater than or equal to 3. Integers greater than or equal to 3. So correct answer is this. Well, this analysis is correct, and this would mean that f is continuous at 2. at 2. But then what about points below 2? Below 2, it is mod x, where mod x is a continuous function. So less than 2 is okay. At 2, we have seen. Greater than 2, it is a function for which you know the points of discontinuity, integers. So you have to look for integers within that domain meaning this. So the points of discontinuities are the set of points of discontinuity is this. Is that fine? What about differentiability? Just from the graph, you can say that, right? Any point of discontinuity is automatically a point of non-differentiability. But what about others? Are these the only points at which the function is not differentiable?
2 also not differentiable, sir.
At 2, it's not differentiable. Anything else?
0.
0 also.
I'll just leave it as this million 0.
It is differentiable.
It's differentiable at what point?
0.
It's mod x. It will not be differentiable. Mod x has a corner.
Okay, sir.
If you want the argument, if you look at f of 0 plus h minus f of 0 divided by h as h goes to 0. So f of 0 is 0. That is mod x, mod 0. So this becomes limit as h goes to 0 of near 0. The definition of the function is it is mod x. So this would become just mod h by h. But if I look at this limit from the left, I would get minus h by h, which is minus 1. And the right-handed limit would be plus h by h, which is plus 1. So this does not exist. Limit does not exist. So it's not differentiable. Is that clear? So graphically also you can see there is a corner, which means you can't draw a slope. You cannot determine the direction of the graph. And you can justify that using the first principle definition as well, where you try to take the limit of this ratio of change in output versus change in input. Both ways you can see that it is not differentiable. Is that clear?
Yes.
Yes, sir.
Okay. Now we'll move on to continue differentiability. The first function that the derivative is asked of is quite routine. At this point, it should be doable quickly. Find f prime. It's a basic exercise in using the product rule. So yeah, at 9 o'clock, just give me the answer.
We can combine the equation and also can solve, no?
Sorry. Will you repeat?
And we can convert this into equation and also can solve, no, sir?
Yeah, that also you can. You can use the distributivity property and then you write it as a cubic polynomial. And then you can differentiate it.
Is it 3x square plus 12x plus 11?
Could you repeat, please?
Is it 3x squared plus 12x plus 11?
12x plus 11, is it?
12x plus 11.
Let's check. Let's wait for one more minute. Let others solve, and I'll go through the solution in two ways, either using product rule or expanding
Yes,
out
sir.
the
I
given
also
expression
think
and then.
this. I also think this is the answer.
Okay. 2 votes, which means it is likely correct. The only way you can go wrong in this question is you just make some calculation error. Conceptually, it is not very involved. All right, let's go through the solution. So if I write, if I look at this as a product of 3 functions, we know the product rule. We know the product rule for 2 functions, not for 3 functions. But we can do it in 2 steps. I can take it as d by dx of x plus 1 times, I'll consider x plus 2 into x plus 3 as one function. If you take any 2 of them, you'll be fine. So this is just, I'm considering this as, let's say, G1, and this whole thing is G2, and I'm doing G1 prime, G2 plus G1, G2 prime. D by dx of x plus 1 is just 1. So on this side, I'm just left with x squared plus 5x plus 6. This is just G2 plus x plus 1 into, if I want to compute G2 prime, I want d by dx of this expression, which in turn happens to be a product. So I'll write it as d by dx of x plus 2 times x plus 3 plus x plus 2 times d by dx of x plus 3. All the brackets closed. Yes. So this is x squared plus 5x plus 6 plus x plus 1 times d by dx of x plus 2 is again 1. So I'll be just left with x plus 3 plus x plus 2. All the derivatives are just 1. We have this plus let me leave it like this. You can expand it out and verify that your answer is correct. But do you see a pattern? Do you see how, if I have f as a product of 3 functions, what would be f prime? What would be the derivative of the product of 3 functions? So I can take derivative of 1, leave the rest as it is. Derivative of the second, leave the rest as it is. Derivative of the third, leave the rest as it is. So the product rule, you can generalize it for the product of n functions and get a nice expression. Can you guess what such a thing would be? Product of n functions.
And the differentiation of first function into
Yeah, so
h
I'll
n
write it
minus
as
1.
something like this. So h1, hi prime, hi plus 1, so on up to h. It's like a complicated way of writing it, but it's compact and it is correct. So you'll have n terms. In each of the terms, only one of the term, which is the ith term, ith function, will have the derivative, and the rest will be as it is. Now, if you expand this out, you should get 3x square, yes, plus you have 5x, 4x, and 3x. 5, 4, 3 is 12, and the constants are 6, 3, and 2. That is 11. Yeah. So this answer is correct. The other way is to expand out the function. What was the last function? It was just 1. Is it? 1, 2, 3. So this is what? X cubed plus. Let me know if I'm making some mistake. 6x square, and the x term will be 5x, 6x, 11x plus 6. Is this correct?
Yes.
Yes.
Right. So here you can just do usual. So this is second. We have the answer. There are multiple ways to solve it. Once again, we get the same result. So that's the derivative. I hope there are no doubts, and we'll go to the next one.
Can we apply here a plus h, the basic rule?
Repeat the question, please.
Can we apply the basic derivative principle, the first principle?
The first principle, you can, it would be very hard. It would be complicated, not hard, computationally. So if you want h going to 0 of f of a plus h, suppose I'm looking for the derivative at the point a, what you have to do is this, right? Now look at the term f of a plus h minus f of a. You will have, so suppose I have simplified my function to, what was it? X cubed plus 6x squared plus
Acha, here we
11x.
can apply, not initially in the starting function. We have to solve it then.
Even you can do it for the original function also.
Just I
But
wanted
then
to
again,
visualize how that would look.
so here everywhere you will get something like a plus h whole cube minus a cube plus 6a plus h whole square minus 6a square plus 11a plus h minus 11a plus 6 minus 6. So these terms are coming from a plus h, f of a plus h, and these terms are coming from f of a. Now the constant term gets cancelled out. Everywhere you will see that the leading term gets cancelled out. So you will be left with something of h times some expression in a involving a and h. If you want, you can further simplify this and you will see that this will be h times something. So when you divide by h, this h vanishes and then.
I got it. But what if I
Yeah.
suppose I apply this basic principle in the first step in the function only without solving the equation? So can I write it a plus h plus 1 into a plus h plus 2 into
Yeah, but
a
then
plus.
how will you proceed anyway? It will be the same thing, right? It will be, you'll have to do something similar. If you want to simplify this, again, you will have to do even more complicated computations.
Mm,
Either way, you will get the same answer. So if I want to look at this by h, I'll use distributivity over here. If you are curious whether or not we'll get the same expression, go ahead. You should. You will. Is that okay?
Yeah.
This question is a bit tricky. Now, f is from 0 to infinity, open. R, f of x is x to the power x. Find times. This is not in the standard form. Remember, take some time. 9:13, we'll resume.
So x square into within brackets log x plus 1.
X square.
X to the power x.
Within x square within brackets log x plus 1. No, not x plus 1. X, log x plus 1, like different terms.
I got x to the power x.
So this is x square, is it? The term on the outside?
Yes.
No,
Sorry,
sir.
x to the power x. I'm so sorry.
Yeah. Good. Hmm.
Couldn't understand my own writing there.
Yeah, any other answers? Has everyone got this answer?
Yes.
Okay, let's take a look at the solution. So what's the problem over here? We know how to do x to the power of a. We know how to do a to the power of x. Here, this is a constant. Here, this is a constant. The base is a constant or the exponent is a constant. But in this case, both of these are variables. So you can't use either of those rules. You can't say, okay, this is of the form a to the x, so I'll just call it a to the x log a. This is not correct. You can't say it is like n into the power n minus 1. This is also wrong. Because those rules are applicable only when either the base is a constant or when the exponent is a constant. In this case, both are variables. So we need something else. So this is not something that will always work. But one way to make the exponent into a product, you know of a way to make an exponent into a product, right? How do you bring the exponent as a product?
By log. By
By
taking
What?
taking the logarithm.
Yeah,
So
but
if I
taking log
have,
on. So, sir, what I need to was take this as y equal to x to the power x, then take
Mhm.
log at on both sides. So that would be
Yes,
log y and
that's
x log y.
yeah, you can do this, you can do this, and go ahead. But what you're doing in the background is like, why can I take log and all that? Is any function I can write as g inverse of f of x, as long as my g is a bijective function. If I have something like this, I can do this, and that is what is actually happening. If I look at f of x, so suppose I have some function f. Can I not write f as e to the power of log of f of x? Is this true? Log meaning natural.
yes.
This can be done, right? Because exponential and logarithms are inverses of each other. So I'll introduce that term. Why do I do it will become clear when you look at the nature of the function f of x. This is x to the power of x. So this is e to the power x log x. Now what we have done is,
I didn't got the first step.
so if you have a number, what is e to the log, yeah, let's say c. What is this equal to?
C.
Is it okay that this is equal to c?
Yes.
So this is what I've done. I've just taken the function and I've written it as e to the power log of x. Why have I done this will be clear. The correctness of this step is clear, right? Mathematical
Yes.
correctness.
Yes.
Now,
Yes,
why
of
did
course.
I do that? Is because exponential functions we know how to differentiate. And by taking logarithms, you will convert it into a form that is more manageable because the exponent it comes out as the product. Now I can do this differentiation using chain rule, product rule, and so on. Right? How would I differentiate this? This is e to the x log x as it is because e doesn't change times d by dx of x log x. I leave e to the x. So e to the x log x, I can once again write it as x to the x because here we have made that this is x to the x. I'll just undo the thing. But d by dx of x log x is something that I know using product rule, which is 1 plus log x. I've skipped a few steps. But is this clear? What might not be clear at this point is why did I choose to reformulate it in this way? And there is no one sort of transformation that will work for all problems. This is why in calculus you can have large class of problems and large varieties of problems.
But sir, taking it as a y equal to x to the power x and then differentiating both sides, isn't that a more
Yeah, you're doing the same thing. If you do
no,
this and
yes,
then you just take log of f of x is x log x. This is another way. And now I can differentiate both sides. I would get 1 by f of x times f prime of x. Once again, chain rule. This is log of f of x. So it will be log of f of x. The derivative will be log prime, which is 1 by f of x times f prime of x. And on this side, you'll get 1 plus log x. If this seems more natural to you, this also works. You will get f prime x is x to the x 1 plus log x. So even in the computation of limits, sometimes you'll see this. So if you can't compute the, or if there is, if there are exponents and stuff, you take the log of the sequence and you see where it converges, or you take the log of the function and see where it converges. Then you take e to the power of that limit, and that happens to be the limit. So this is a taking the log and then reversing it is a standard technique when you have exponents and which are not in standard form. Standard form meaning a to the x or x to the a. Is the answer clear? Why it is so?
yes.
So the reason why I prefer this is because this is sound within, okay, even in this case, this is also okay. If I take the log is a differentiable
No,
function,
but
f is a
I also
differentiable
thought of
function.
doing it like this, but this just seems a bit more uh, complicated because reductive as well, because you are converting into an exponential form, then reducing it back to original form. And on top of that, you are also using chain rule in the same
The chain
term.
rule will
So
be used anyway. So even
yeah,
over
yeah,
here, you're using
no,
chain rule.
but when you are doing it to different sides, like you're using an RHS and an LHS, it's easier to. I mean, right now this question is not that difficult, but in general,
Right, e to the log being the identity function is also okay, right? So that is the same thing.
oh yeah, it's the
It is
same
not,
thing.
these
I
two
mean, yeah,
things
people.
are not very different. In the case of sequences, for example, if I have something like an, I want to find the limit of an, there are places where you take the log of the an and then see where it goes to, and then an goes to e to the c. I'm not sure if you have seen examples of this sort or not, but here in the background, you will have to justify all of these things. You have to say why an would go to e to the c if log of an goes to c. There is a continuity argument and all that. There are certain things that need to be justified when you do things like that. But writing an expression as f of f inverse of that expression for a good choice of f, you can do it anyway, and then you can use the properties of the derivatives. So in this case, both of them don't have much justification to do. Both of them are fine, but it's just a style choice.
Okay, thank you. So I just had a doubt about the quizzes and how they are graded, right? So
Okay.
I was checking the grading document, and it had two distinct methods to calculate the final grade, right? One is where the marks of maximum of both the quizzes is considered along as 40% and 60% of the comprehensive. And the other was that 25% of quiz one, 30% of quiz two, and 40% of comprehensive, or something like that, 45%. Which is the method that is generally used?
Your score is calculated in both ways, and whichever is higher is taken.
Hmm. Okay.
Okay, so if for whatever reason a student misses or does not do well in one of the quizzes, one of the formulas will work better, which only considers one of the quizzes for 40%, and then the 60. I don't know the exact numbers. I'm not, I don't remember the exact numbers. So if you do badly in one of the quizzes, one of the formulas will work better for you. And if you do well in all the quizzes, it's the other formula will work better. But in any,
Attending both the quizzes is not like for some reason, if
it
someone
is
misses the
compulsory.
second, it is
It
compulsory,
is.
right? But if someone misses the
You
another
check the
quiz, then
grading document. I'm not uh, aware of the precise rules. There is some eligibility criteria and all that. It should be
Hmm.
detailed clearly enough there.
Okay.
All right. This is what question number 7. Once again, we have this piecewise defined function. It is defined as a plus bx squared plus differential. We have seen such problems. Now, do for differentiability. 930.
So A2 and B3.
Let's wait.
Someone has given a different answer in the chat box.
Okay. I don't have the chat box open, so please speak up. Or if someone can tell me if there are people answering my
Someone
chat
has
box.
mentioned 1 and 2 in the chat box.
Anyone else? Okay, let's go through this thing. So either of you, 1, 2, or 2, 3, can you tell me how you arrived at A is equal to that and B is equal to the other thing?
Sorry.
Could you explain your solution?
Yeah, so I checked continuity at 1, left for the left value and for the right value. Then equaled both
Okay.
of them. And so I got my first equation as B equal to A plus 1.
Okay.
Then I tried for equal derivatives at x equal to 1
So
and equal derivatives at x equal to 1 and got another equation from there 2b equal to 3a. Solve the two
okay,
equations.
that's the correct way to do the thing. The trap that this problem tries to highlight is the following. When you say it is differentiable, you could go directly to try and compute this sort of expression. Uh, at every other point, irrespective of what value of A and B you take, differentiability will not be a problem. They are polynomials. So I am only interested in x is equal to 1. So I would look at something like this. But then, what is f of 1? That is given by this expression. So I could try and do the left-handed limit and right-handed limit of this. So at the left-hand limit, this would be A plus B times 1 plus h the whole square minus f of 1 is something like 3a minus b plus 2 divided by h. Limit as h goes to 0 minus b plus h square b plus 2hb minus 3a minus b plus 2 divided by h is a b that gets cancelled. But now you see there are terms which involve h and there are terms which do not involve h. Let me write that down even more clearly. You want this limit to exist. When would this limit exist? Which be minus 2a plus 2. If I have not made any calculation mistakes, but I have, correct? I have made some calculations. So this should be plus b minus 2. Minus f of 1, no, 3a minus b plus 2 minus 3a plus b minus 2. Wow, wow, wow. Let me makes things different. This is once again a more complicated way of doing it. I'll show you the easier way also. So suppose you have this expression now. When would this limit exist?
When h is 0.
No, you're computing the value of h. Computing the limit as h approaches 0. So you have an expression in terms of h in the numerator, and you have something in the denominator. Now, if I substitute h in the numerator and the denominator, what happens? What happens to the denominator?
This will eventually tend to infinity.
The denominator will go to 0. So the expression will go. There is a possibility that the numerator also goes to 0. That is the only case when the limit can possibly exist. So if I have something like limit as x goes to 0, x plus 1 by x square or something. So what is the limit of this? Does the limit exist? Does the limit of this expression exist? That should not be a difficult question to answer.
1.
The numerator goes to 1, but the denominator goes to 0. So what would the expression of the, what would be the limit of this expression? So this is not defined because this becomes arbitrarily large.
I'm sorry, sir, I couldn't hear you. I got disconnected. What's that?
So this limit does not exist.
Yeah.
Okay, so but just because you have a 0 in the denominator, it doesn't mean your limit will not exist. There are cases in which the limit exists. Does the limit of this expression exist?
Yes, sir.
Yes, and it is one of the standard identities, and it is equal to 1, right? What about this? Does this limit exist? This is a known limit.
It's 1.
1.
One.
Yes.
Yeah, it
1.
exists and is equal to 1. What about this?
Sir, doesn't exist.
This doesn't exist, right? So if you have a numerator which goes to a finite value and a denominator which goes to 0, the limit will not exist.
Sir, but we are doing this by L'Hospital, right? I mean, if we apply L'Hospital, then eventually we can.
So in order to apply L'Hopital's rule, you will have to have the numerator also go to 0. So you cannot apply L'Hopital if it is not in a 0 by 0 or an infinity by infinity form. So if you have something
But
like
for
this,
sin x by x, we are applying L'Hopital rule, right? And
okay,
if it,
you could do that way. There is a way to do it without L'Hopital also. But for cos x by x, you can't use that. Right? So if I have limit as x goes to 0, cos x by x, I cannot say that this is the same as derivative of this by derivative of this. That would lead you to a wrong answer. You can use L'Hopital only when you have 0 by 0 or infinity by infinity, which in this case it is not. So whenever you have the numerator going to a finite value and the denominator going to 0, the limit will not exist. In this case, this does not exist. So what is happening over here? Now back to our original problem. You have the denominator going to 0. And you want the function to be differentiable. Correct?
I'm sorry, sir, but I just lost the chain of thought. What are you explaining here with this limit of h square b to h minus 2 by 2?
We are trying to see whether the function is differentiable. For that, I take the first principal argument. I say f of 1 plus h minus f of 1 by h, this limit should exist. This exists. Since I am demanding differentiability, by definition, this is what
And
should
you're
happen.
taking it at x equal to 1.
Yes, at x equal to 1.
Okay.
Because that is the point of interest. At other points, we have differentiability for free. So it is f of 1 plus h minus f of 1 by h as h goes to 0. So first I
So you're
look at the
so you're
left-hand limit.
solving it using first principles.
Yes.
Okay.
Okay. So this expression, I'm trying to calculate the limit of. If the limit, I want the necessary condition for differentiability is this limit exists. It is the equivalent formulation. So if this limit exists, its left-hand limit also exists. So on the left, I wrote f of 1 plus h as a plus b times 1 plus h square using this definition. And f of 1 by definition is 3a minus b plus 2. So I substituted that as well. And then I simplified and I got this expression. Now, when would this limit exist? Following this argument, if I have a numerator which does not go to 0, would this limit exist? So the limit of the denominator is 0. What is the limit of the numerator? If I substitute h equal to 0, what will I be left with?
It would only exist if this minus 2a plus 2b minus 2 would be 0.
Yeah. Let me write. The above limit exists only if, well, I can't say it exists, would exist. It's actually exists itself. Only if minus 2a plus 2b minus 2 is equal to 0. So this gives me the equation a minus
Equal to
b. No, right? A minus b
is equal
plus
to
1 is equal to 0.
plus 1. Yeah.
Okay, so this is one equation. Is this one of the equations that you got? If I've not made any errors, yeah, they should be fine. I think both
Yes,
of
sir.
your
This
solutions.
is yes, this is essentially. I just wrote it as
Yeah.
a plus 1, b equal to a plus 1.
Yeah, that's fine. So the other thing, limit as h goes to 0 plus also should exist, right? So, okay, first of all, in this case, what would the left-hand limit be? If this is 0, you will be only left with h square b plus 2hb divided by h. And that limit exists. That is just hb plus 2b, which will go to 2b. Is that correct? This is the left-hand limit when you're doing the derivative computation. Now, when you're doing the right-hand limit, you'll have to use the other expression. 3ax minus b plus 2. So 3a, x is 1 plus h. I'm doing f of 1 plus h minus f of 1 divided by h. This limit also should exist. But in this case, since the function value is the same, here you will be in slightly better shape. only 3AH will be left. Isn't it? Everything else gets cancelled, divided by H.
Yes.
And this, irrespective of the value of A or B, this limit will exist and will be equal to 3A. Now, if this limit exists, the right hand limit and the left hand limit have to be equal. So I got the left hand limit as 2B, right hand limit as 3A. And I get 3A is equal to 2B.
So, sir, I'm so sorry
Is
to
this
ask, but it's just that why, like, you solved it using first principles, but why, like, this is
yes?
essentially a more complex method to do it, right? Like, than using continuity where you just have to put the value of one and get the
Okay, if you use continuity, you'll get one equation, and for the other equation, what do you do?
differentiated this derivative at one, at x equal to one.
So derivative at x equal to 1, you have to show that you have to, if you're assuming it is differentiable, this will, so I'm assuming you're doing something like 2bx, and then you're looking at 3a, and then you're substituting x is equal to 1 and equating these two.
Yes.
So that assumes that limit of f prime x as x goes to 1 is equal to f prime 1, which would require more than differentiability. It is even asking for the derivative to be continuous. It's a subtle point, but computing the derivative to the left and taking its limit, this is something that we discussed earlier also, need not always give you the value of the derivative at that point. It can happen for a function that it is differentiable, but if you take the limit of the differential
But
of the
sir, if
derivative
the
away
question
from that
suggests
point,
that the question, sorry to cut you off, I'm so sorry. I was just saying
that's
that
fine. That's fine. Go ahead. Yeah.
the question suggests that we have to find where f is differentiable, right? And I get what you're saying, but if it is asking for
Yes.
where it's differentiable, then essentially it means that the left will be equal to the right, right? Correct.
In this case, yes, because we have polynomials. They are infinitely differentiable. But this differentiability does not imply f prime x will go to f prime 1. Okay, maybe the last question that we'll do, I'll highlight this point. But in this case, you can do a plus bx as the derivative on this side, 3a as the derivative on this side, substitute x is equal to not a plus bx, sorry, it's 2bx as the derivative on this side, 3 as the derivative on this side, equate it at x equal to 1. But that needs a justification. That point may not be clear to you why that requires a justification. And in this case, the justification is simple because you have polynomial functions because a and b are
Sir, how I justified it to
constants.
myself was what I just told you, that as if we are looking for differentiability, then essentially it implies that the left differentiability at one will be equal to the same at for the right side.
Yeah, what is left differentiability?
Essentially, I
So
mean that a plus bx square, when it is differentiated, will be at x equal to 1, will be same as 3ax minus b plus 2 at x equal to 1 when it's differentiated.
So, okay, let me write that statement. A plus bx square when the the derivative at x equal to 1 is equal to 3ax minus b plus 2. The derivative at x equal to 1.
Considering that fx will be differentiable.
Yeah. Just give me 1 minute. Okay. I will tell you that this in general need not happen. I'll give you an example as to why. The next question will be that. This is the more principled approach. This is the correct approach. But if you have nice enough functions without any denominator, without any vanishing, you can do that as well. So I'll take this function to drive home my point. We did discuss this yesterday, but I'll change it a little bit. And so this is x less than 0. This is x greater than or
You
equal to
can
0.
solve the previous question in a shorter manner.
Also,
Shorter.
sir, considering that they are continuous, then this statement will in itself be true, right?
This statement will not be true in general.
But if it is continuous, if the function is continuous, then it should
Even if the
then
function is continuous, it need not be true.
oh,
Yeah. So here what you're essentially asking is f prime x, the limit as x goes to 1 minus is the same as limit as x goes to 1 plus of f prime, isn't it?
yes. Yes, this is
Just
exactly what. Yes.
continuity of the derivative. For the continuity of the derivative, okay. Now
Sir,
I'm a little bit confused.
if f is differentiable, then f
Mhm.
will be continuous also, right?
F will be continuous, not necessarily f prime.
Haha. So that is what I think he was saying here. So just because this is polynomial, we can just put the value for finding the limit. So
For the polynomial, it is infinitely differentiable and this will hold. That is what I said, that justifying this for a polynomial is okay. But what I'm trying to emphasize is this will not work always. This is not a statement that will hold always. And I'm trying to come up with an example. I think the example that I've written down as question 8 will work. An easier way to solve this problem is first identify that it has to be continuous and reduce one of the variables and then do the same thing. That will give you a faster way to solve it. So for continuity, what will you get? You will get a plus b is equal to 3a minus b plus 2. So you will get this a minus b plus 1 is equal to 0. This equation that we got after all this work, you will get it for free with if you just use continuity. Okay. And then if I substitute a is equal to b minus 1 and write it only in terms of b, then you will see when the slopes of the function have to align with each other, and then you can do it that way. If you have polynomial functions, please do it this way. First verify continuity, you will get one equation. Then you compute the slopes on either side and take the value at that point. You will get the other equation. I leave that as an exercise because of time. But just to demonstrate the point that I was making earlier, I will do this. Now, what about this function? What is the derivative at 0? Does the derivative exist? Is it differentiable? Is it continuous? Is the function continuous, first of all?
Sir, it will be
Yes,
differentiable.
it is continuous.
Is it differentiable?
Yes, sir, it will be.
How will I prove that it is differentiable?
Sir, we can find the LHL and
Sir, I mean, we
RHL.
can use the, sorry.
So, and then we can equate that. So RHL will be getting, I guess, 0.
RHL of what? Right hand limit of what expression?
Uh,
Sir, f dash 0 going towards 0 positive equal to limit h tends to 0 plus h
Okay,
square
let's do the thing that you were suggesting. Right? Let me do this. This will be simple. Okay, first, let me write this. F is continuous. One way to see this is by sandwich lemma. For the LH, for the left-hand limit of the function, you can use sandwich lemma. Sign is between -1 and 1. So x squared sine 1 by x is between minus x square and x square, both of which go to 0 as we approach 0. So the left-hand limit is 0, the right-hand limit is 0, the function value is 0, and we are good. If you have not understood, take this as an exercise. Now, differentiability. If I go about doing differentiability as you have suggested, I take this quantity.
So this is a more complex function to differentiate essentially.
Yes, it is. And
The
that's
right
why,
hand side is right hand is still more easier. I mean, obviously it's more easier, but considering the left hand side, you
F
have to, I
prime,
think,
sorry.
take absolute values for h or something. I don't know.
Sir, I guess yesterday we have we have done this question, right?
Yes, we have done this question, but since it doesn't seem clear yet, I'll tell you this. This would be limit as x goes to 0 minus of sine 1 by x times 2x. So if I differentiate this expression plus, or it would be minus cos 1 by x. If you do the thing, you'll get this. Does this have a limit as x goes to 0?
Sir, this is what you have directly differentiated, right?
Yes. So
Then
when I'm considering x goes to 0 minus, I'm looking
okay.
at the behavior of the function to the left of 0. So I'm not at 0. So I'm over here. And the suggestion was that you differentiate it over here and take the limiting value of the slope
Yes,
in
sir.
order to find f prime 0. But does that exist?
So this-
Cos 1 by x will keep oscillating.
Yes, sir.
It will not converge to any point as I approach 0. So this limit does not exist. But if I do the limit as h goes to 0
Sir,
of f of 0 plus h,
there.
just let me complete this.
Okay.
Let h goes to 0. Sorry. Limit as h goes to 0. F of h, whether you're on, if you want, let me do minus because plus is easier. H square minus h square sine 1 by h. If you're doing it from the positive side, this sine 1 by h also will not be there, divided by h, and this becomes h sine 1 by h, which again is by sandwich principle equal to 0. So this limit exists similarly limit as h goes to 0 plus of f of 0 plus h minus f of 0 divided by h exists. Therefore, f prime 0 exists and is equal to 0. But what you have claimed over here, this identity that limit as x goes to 1 minus f prime x is equal to limit as x goes to 1 plus f prime x, those two things are equal, is not true in general, is what I'm trying to say. With this example, what I'm trying to say is one of the limits might not even exist. So this is why this is a more principled approach. What I've written over here, either use continuity to get this, but even then you will have to analyze this limit if you want to do it very precisely mathematically, or you have to justify why this equation will hold. In this case, it is easy because it is infinitely differentiable because these things are polynomial functions. So you can go that way too, but that would require more machinery. I am saying that with the machinery that you have, just using the fact that limit of a certain thing exists, if you want differentiability, you can get the answer. Whether it is practical to do in an exam or not, all those things are, yeah, you prepare for your exam accordingly. But as far as mathematical correctness goes, this is a sound approach, and this is not something like this where you have two ways, both of which are correct, which is a style choice. This is a dangerous thing to do by default. May not be when you're dealing with like normal functions in a data science course, but in general, when you have functions of this sort, it might not be true.
Okay, sir. Thank you so much.
All right. Is this clear? Why this and do you understand what the gap is? Why this need not be true? You can have a differentiable function for which the derivative is not continuous. What is this essentially? This essentially is the condition for the derivative function f prime x to have left hand limit equal to right hand limit. Right, which is talking about the continuity of the derivative. That need not be guaranteed. All right. So I
sir,
think
it
it's stop over
essentially
here.
fails when the behavior around 0 is not predictable.
Even if it is predictable, like predictable is once again a subjective term, right? So even if you just say x squared sine 1 by x and you just take 0, the function that we considered yesterday, even for this you'll encounter the same problem. So is this predictable, not predictable? So there are ways in which the derivative need not be continuous, is what you have to see. And if you can assure that the derivative is continuous, then that method works.
So I don't know, sir, why I thought generally if a function is continuous, then the derivatives would be the same for both sides. But thank you for the clarification.
Yeah, and once again, I'm going to emphasize this. The functions that you encounter while you're doing any data analysis or algorithms will typically not be in sine 1 by x sort of form. It'll be polynomial functions and so on.
No, yes,
So
but right now
you
we are
probably,
discussing
yeah.
mostly.
In the context of purely math, it is
exactly.
important to note that where you can go wrong. Not necessary to break your head a lot over it. But yeah, it's an interesting example mathematically.
I mean, it worked for me there. Like maybe I got the correct answer there, but
Yeah,
I mean, if we won't
it
have
is good to
discussed
know
this,
that
then I
it will
might have been
not
wrong.
be. Yeah, yeah.
Yeah.
Okay, cool. I think we'll wrap it up over here. We have done, okay, 6 questions, but there were sub questions within those 6 questions. I think we have covered enough. Not there will be revision sessions and
I
other
don't know,
ways
sir. You
to.
said you would cover something in the last local behaviors of something. I could not.
Okay, that I will not spend too much time on. Once again, this is something that would be interest to yeah, the mathematical understanding of things. Now, what I'll quickly say that. So if I want to say, let's say I have a function f from R to R, I am interested in differentiability or continuity. Continuity, differentiability at x equal to a. There is some a. What I need to do is I can just look at the function in some small interval of this form. Whatever epsilon you want, you can take a small epsilon. You can look at the function in this. If it is differentiable over here, it is differentiable over here. So the behavior of the function away from points close to a doesn't matter. Why I made this comment was when you're talking about piecewise functions, the sort of functions that we considered over here, how do I say that it is differentiable at, let's say, 1, at x equal to 1, for example? I have some behavior of the function elsewhere. Look at just minus or half to 1.5. What is the description of the function from half to 1.5? This function itself, I'm just restricting it to a smaller interval. Look at the definition of the function and tell me how it is defined from half to 1.5. Which definition applies of the 4?
So this third one.
Yeah, so it's x square plus 3. Now, if I just tell you the function is x square plus 3, do you not automatically say that it is differentiable? It's a polynomial function. It is differentiable. At every point on the domain, it is differentiable. The domain being 0.5 to 1.5 for now. And that would mean that this function, the original function, which is defined from R to R, is also differentiable at 1. So if I want to look at differentiability at 1, all I need to do is look at it in an interval around 1. That is why these points other than these 3 points, I can safely say that this is continuous or differentiable also in this case, because locally or in an interval around those points, any point you take, you can find a small enough interval where it behaves like a polynomial. So this is what I meant by differentiability is local. So I'll just leave it at that. Does that clarify your doubt, at least in some capacity?
Yeah, so essentially, I think you said that the differentiability or continuity of a point is depends on the local behavior, right?
Yeah. Considering this is sufficient. Because what do you do when you are looking at continuity or differentiability? You're looking at quantities of this form. limit as h goes to 0 of f of a plus h, something like that. Now, you're only interested in h goes to 0. So for arbitrarily closed points, only that behavior matters. For the limiting quantity, even in the case of continuity, you'll say limit of f of x as x goes to a. What do you mean by that? You're only looking at points which are very close to a. So if there is a polynomial behavior of the function at all points close to the point of interest at a, let's say, what do you mean by close to? The formal way of saying close to is there is an epsilon neighborhood, meaning an interval of the form a minus epsilon to a plus epsilon, where it behaves in a certain way, in this case, a polynomial function. Then continuity, differentiability, all of that follows. Trivial. So that is the justification for why we are just considering these 3 points. Was there any other point that was left out for the end of the session? I suppose not. This is all okay. This is also okay. Okay. If there are any doubts, I'll take 1 or 2 of them. Otherwise, we'll wrap it up.
Thank you so much, sir.
Okay. In that case, we'll stop now. Thanks, everybody. Good night.